says something stupid or inappropriate.
What about like before that?
What do you
Not-
define as inappropriate?
I mean, you could say something stupid or inappropriate and just blame it on Becca, because we didn't specify which Becca. So.
Becca Blair.
All right. Yesterday, we went through phase changes and talking about things changing state from one state of matter to another state of matter. In order for that to happen, regardless of which change of state occurs, what has to happen to the particles, the molecules or atoms that make up that substance? There has to be a what? There has to be a change in energy, right? It can either go up or it can go down, but there has to be a change in energy. Specifically, that energy is generally thermal energy, but we haven't really introduced thermal energy yet. Probably because you know some English, you know it's probably going to deal with what? Some things that are warm, right? But let's talk about them a little bit more. As it says up here, today we're going to introduce 3 words. Those words being heat, temperature, and thermal energy. They sound similar, but they are different. So like it says right here, right, know your definitions, okay? First definition, not a new definition, one that we've covered, I don't know, 854 times so far, right? We've already established that energy is what?
The ability to do work.
That's
Dude,
really-
dang it! Becca Blair, put it in my head, kid.
The ability to do damage, the ability to move or change matter, the ability to cause change in something else. As we've discussed, that ability to cause change comes in a lot of different forms. One form that this unit focuses on is thermal energy. So thermal energy is the energy associated with the movement of microscopic particles that make up an object. And that line isn't quite long enough. Actually, I think there's supposed to be another line underneath it that I forgot to highlight for you. So first, to clarify, when we talk about microscopic particles, what microscopic particles would we be talking about here? Could be atoms, or it could be molecules, depending on whether we're talking about an element or whether we're talking about a compound. The fact that thermal energy is associated with movement means that really thermal energy is a kind of what? It's a kind of kinetic energy. Okay? Now it's kinetic energy on a real small scale, because remember, kinetic energy depends on the movement of particles. Generally, we think of kinetic energy being the movement of something big, but here we're talking about the movement of something small. That probably could be waited until the end. That's probably pretty vital that that happened right now. So, that wasn't distracting for anybody at all.
To clarify, Nicole just got up in the middle of class to throw out a piece of paper.
It's bothering me.
Let's clarify even more. Instead of just getting up in the middle of class, ran across the front of the room,
Did a lap.
put the paper,
For the
and
folks
then
at-
completed
for the
lap.
folks at home.
Right, so, yes, to clarify. So, all right, let's start getting into some new terms. First, heat. Okay? Heat is defined as the transfer of thermal energy from one object to another because of a temperature difference. Transfer of thermal energy from one object to another because of a temperature difference. Which way is thermal energy going to flow if we talk about a temperature difference? It's going to flow from
Hot to cold.
hot stuff to cold stuff. Okay? Heat will flow spontaneously from objects with high temperatures to objects with low temperatures. What does spontaneously mean? Have we come across that one in vocab yet?
We come across sporadic.
Spontaneously is different than random. No, it's not random. Okay?
Out of the blue.
Spontaneous means suddenly or on its own. Okay? So you don't have to do anything for energy to flow from hot stuff to cold stuff, right? if you mix cold milk into hot coffee, energy will transfer from the hot coffee into the cold milk. You don't have to do anything to make that happen. When does this stop? When does heat stop? What? When they're equal temperatures. We refer to that as thermal equilibrium. Okay? When they're the same temperature, that heat transfer or the energy transfer will stop. For example, if you put a cup of hot coffee on the counter and you let it sit there all day, what is it going to do?
Room temperature.
It's going to get cold until it reaches what?
Room temperature.
Room temperature. Will it continue to lose energy after it reaches room temperature? Will it eventually turn into an ice cube? No, that doesn't happen. Energy transfer occurs because of a temperature difference. If there is no temperature difference, there will be no energy transfer. Okay? Good there? All right. Temperature. Because we use temperature to define the last one, let's make sure we know what temperature tells us. We've already sort of mentioned this. What does temperature tell us about an object? It measures the movement. Specifically, it measures the kinetic energy, okay, which is related to movement. Okay? But yeah, Savannah, that's the idea, right? Which underneath there it says which relates to the movement of the particles. Okay? But one thing I want to make sure that you understand is that if we have two substances that are at the exact same temperature, if we have water at a certain temperature and rubbing alcohol at a certain temperature, they don't necessarily move the same speed because kinetic energy also has a mass factor thrown in there. So you have to kind of take that into account. Okay? But generally speaking, right, cold temperatures have less motion, high temperatures have more motion, right? And if you look at your outline, sorry, I should have put this outline up. Stand by. People at home, stand by.
Or sit down. It might be a lot.
Oh, you should sing a song.
Wait patiently. So on your outline, underneath temperature, there is this question, right? And it says, why the particles in the container on the left have shorter lines than particles in the container on the right? Well, the fact that the container on the left has ice cubes around it means that its temperature is probably what? Colder than this one that has flames shooting out of it, right? That being said, right, higher temperature, longer whoosh lines, right, indicating that these move faster than these ones. We okay there?
Yes.
All right. Now that we've introduced both heat and temperature, and we use temperature, oh sorry, finish writing stuff down. As we've introduced in the first two terms here, heat and temperature are related to one another. Let's talk about how they're related. And let's use these billiard balls as examples. Okay? So, 9 is the yellow striped one, 2 is the blue one. Okay? Let's say 2 is sitting still on the table, 9 comes rolling in. It runs into 2. They bounce off in different directions. Okay? But from an energy standpoint, before the collision, right? Before the collision, where's all the energy? In A, or in the 9 ball, right? It's moving, but 2's not. Now, this isn't totally representative of particles, because do we ever have a situation where particles aren't moving? No. But from a temperature standpoint, what would the 9 represent? High temperatures or low temperatures? High temperatures, whereas the 2 would represent low temperatures, right? Now, that being said, let's go to after the collision. Okay? So after the collision, what happens to 2? From an energy standpoint, which how about it goes faster, right? Because it was sitting still, but now it's moving. So, from an energy standpoint, what has happened to 2's energy? It increased, right? But for that to happen, what had to happen to 9? It had to slow down, right? Because of the whole conservation of energy thing, right? If 9 has all the energy before the collision, but now it has to share energy with 2, it's got to slow down. How does this represent heat and temperature difference? We said that 9 represented things that were hot. What happens when hot and cold things are mixed to the hot thing? It cools down, right? 9 was going fast, now it's going slower. But what happens to cold things when hot and cold things are mixed? They get warm, right? 2 was not moving, now it is moving, right? So, at the bottom of your outline, it says, how does these billiard balls explain the whole idea of heat and temperature difference, right? 9 is a hot thing. It slowed down and got cooler when it ran into 2. 2 is a cold thing. It sped up and went faster after it ran into the hot thing. Does that make sense? After a collision, things that were going fast, things that have high temperatures, end up going slower. Things that were traveling slower, things that have low temperatures, end up going fast. And we said that will continue as long as what? As long as heat flows from hot to cold. So when does heat stop flowing from hot to cold? When they're the same temperature. And we call that thermal equilibrium. All right, good there?
No.
Okay. Well, looks so exciting. I just wish I just hope your excitement comes out of the recording so people understand how it works. That'll come from the recording. So. All right.
Do it without looking right now. You didn't even click it.
You can click anywhere on the board.
All right.
That's not even fair.
I should have thought that through.
To
All right.
clarify, neither
Third
one of the
turn.
Beckers knew that.
The third term that kind of sounds similar to those first 2 terms but is different tells us about thermal energy. Thermal energy takes into account the total amount of motion of the particles that make up an object. Like we said, when we talk about particles, that could mean what? Could be atoms, or it could mean molecules.
Compounds?
Well, compounds are made up of molecules.
Boom.
Right?
Yeah, they are.
Now, if we're talking about the total amount of motion, what do we have to take into account? What factors are going to affect the total amount of motion?
Attraction.
Say again?
Contraction. Maybe.
Yes, although
That's
that,
been a
okay, so
popular
the
answer
attraction,
lately.
that kind of gets into what?
What?
We talk about attraction, we said that sort of affects the what?
State.
The state of matter. So that's one thing we have to take into account. What else? The temperature, how fast are the particles moving? Again, what you said. The mass, all right? These 3 things will go to influence how much thermal energy exists in an object or a sample of substance. Mass takes into account how many particles are actually there. Temperature takes into account how fast are those particles moving. And then state of matter takes into account things like forces of attraction and stuff like that. Okay? All of those will influence the total amount of motion. Okay? All right, good there?
Yes.
Okay. Couple of pictures to help us understand these concepts. First, before you write anything down on your sheets, Okay? This, what I'm going to talk to you about now, does not relate to your sheet. Okay? According to these two pictures that are up on the board right now, what can you tell me about the temperature of the water in the teacup versus the temperature of the water in the bucket? Okay, Katie, go ahead.
The temperature in the teacup is hotter than the one in the bucket.
Okay, the temperature in the teacup is hotter than the temperature of the bucket. What does that mean? Okay, Katie, go ahead.
That the particles are moving faster.
The particles in the teacup are moving faster than the particles in the bucket because they have a higher temperature. But does that mean that there is more thermal energy in the teacup than there is in the bucket? Not necessarily, because what don't we know, Becca? We said what other factors influence the thermal energy? The mass, state of matter. It looks like the state of matter is the same, but the mass is definitely not the same. So, don't write this down, okay? But in this case, cup has a higher temperature than the bucket. That means that the particles in the cup are moving faster than the molecules in the bucket. But we aren't sure about which one has more thermal energy because we don't know the exact temperature and the mass and stuff like that. Okay? Is that good? All right, now, let's get to what your outline actually says. So your outline goes and makes an assumption, which is always a dangerous thing to do, right? Even though the picture doesn't reflect this, it says the water in the bucket and the water in the cup have the same temperature. If that's the case, what does that mean? If they have the same temperature, Katie, that means what?
That they have thermal equilibrium.
Yes, that's true. What does it mean about the molecules?
Oh, they're moving the same.
Okay, that the molecules in the cup and the molecules in the bucket would be moving the same speed. The picture doesn't necessarily reflect that, okay? But if it was the case that if they were the same temperature, that means that the particles would move the same speed. Now, keeping that assumption, can we now assume which one has more thermal energy? Yeah, which one? The bucket's going to have the more thermal energy because the particles are moving just as fast, but how many molecules are in the bucket versus the cup? A lot more, right? So the bucket would have more thermal energy because it has more mass. Whereas before, we said we couldn't really assume which one had more thermal energy because we weren't sure about the difference in temperature versus the difference in mass, et cetera, et cetera. Okay, Joe, go ahead.
What is the first, like the red? What is that?
Oh, molecules.
I know, but like the whole thing.
Molecules, move same speed. Sorry.
Is like an autocorrect using like
Yes.
autocorrect like his spelling? Like type it once you
Do we just skip the part with the sparks?
No, we're doing spark plug.
I have those
All right, we good with those?
Yeah.
Okay, let's talk about the spark plug.
I have those. Can I bring them in? Oh, I thought it was a wand.
Nope.
It really got me going. That's like the entire Harry Potter.
Okay. So, do the sparks that come off the sparkler have a high temperature or a low temperature? They have a high temperature. What does that mean? The particles move very, very fast. But, do the sparks that come off the sparkler have a lot of thermal energy? No. How do you know? So not a lot of mass, but also just from personal experience, okay? I'm assuming most of us have probably, 4th of July sparkler thing, right? Okay. So if one of those sparks hits your hand, does it hurt?
No, we don't feel him.
I mean, hurts a little bit, right? But overall, does it do a whole lot of damage to your hand?
No.
Not really.
So it's low
Right? So it has a low amount of thermal energy, even though the individual sparks may have a high temperature. Good there? All right. I know it's sucking.
Where's some wood?
Don't speak the words.
Oh, that was probably really
All right. So next two, thermal expansion and contraction. Okay. Because you know English, you probably can figure out what goes on here. Okay.
You should be. That's
Come on.
awesome.
Based on the motion of the particles as the temperature changes, volume will also change.
Wow.
Generally speaking, not always the case, but generally speaking, things that have a higher temperature will increase motion, right? That's the higher temperature part, and that generally means larger volume, right? So as temperature increases, motion of the particles increases and the volume increases. Okay? If you just want to use upwards arrows, you can do that too.
Man, I'm gonna lose.
So that means, oh, and that means as the temperature decreases, less motion, volume decreases. So,
Are you just writing each
I
thing?
want some.
all right, so, hold on. Hey, freeze. You've got like 3 minutes. So first, as far as calendar is concerned, on the calendar there's a reading assignment for you both, a couple pages that deals with these ideas of heat, thermal energy, and temperature. Okay. Also some questions from the book that relate to these topics, so it might be a good idea to start looking those over. Okay. Tomorrow we will get into energy transfer and how we get this energy, this thermal energy, to move from one place to another. Good job, everybody. A whole outline. Well done.
And it's recorded and everything.
And it's recorded. I made a good choice
Wait,
today.
did you stop it yet? Remember this day.
No, I don't
You
think
finished
so.
it online.
Yeah,
Yeah,
yeah,